Doodling with Mr. Brewer. Alright, today's lesson on Doodling with Mr. Brewer, we have got vector addition. Now, we've talked about vectors. We talked about vectors having both magnitude and direction. That's what makes them different than a scalar. Now, what I want to do today is I want to talk about really how we're going to draw the vectors, how we're going to represent them most of the time with arrows. So we're going to draw the little arrows. They might be pointing in different directions, but all of them are pointing in directions. Okay, so if I want to take a vector and I want to add them, we have a thing that's called tail to tip. Okay, so I'm going to take the tail of one vector and I'm going to add it, but I'm going to add it to the tip of the other arrow. So I'm going to give you an example. Bob walks 27 meters north. Now how I'm going to represent that is I'm going to represent it with an arrow. So I draw my arrow. I'm going to label that thing. So he's walking north. We're going to represent that as going up on our coordinate system, and that's going to be 27 meters. Now, Bob is going to get to that 27 meters, and then he's going to stop, and he's going to turn. He's going to turn and go 36 meters to the east. Now, I'm going to have to draw that, so I'm going to represent east this way. Now, it's going to be longer than the first one, so I'm going to fix that. There we go. So that's 36 meters. Now, I've got two separate vectors there. When I add them together, we're going to end up with what's called a resultant vector. So what should I do here? I'm going to take that 27 meters. I'm going to add to the tip of that the tail of the other one. So we come across right there. So we have 36 meters in this direction, and we're going to call that's at 0 degrees. And this one is going to be at 90 degrees, and it's 27 meters. Alright, when I add those two together, I can graphically represent that really easy, and I can show a resulting vector. Okay, and that's what they call this. They call that the resultant. Ta-da. Okay, now I can solve for this. We can use the Pythagorean theorem, and we can actually solve for this particular problem. I'm not going to take the time on this one because I hope you guys have been through geometry. But we're going to get beyond this, and we're going to actually add multiple vectors together and see how we actually solve for that. So I'm going to give you some examples. Alright, so we're going to go on a little bit of a hunt. Okay, so our first stop, we're going to go on a hike. We're going to go 1.7 kilometers. We're going to go a little bit further, and we're going to travel at 37 degrees east of north. Okay, we'll draw that out as an individual vector here shortly. Okay, and then we're going to take a little bit of a bird walk, and we're going to go 0.9 kilometers. Yes, that's my 9. And we are going to go 14 degrees south of west. Alright, from this point, we're going to take another turn. Here we're going to go 4 kilometers. We're going to make it a little bit easier on you, though, and we're going to go at 90 degrees north. So what that means is we're going due north. Okay. And then the bottom one, the last one that we're going to do is going to be 2.1 kilometers. And that is going to be at 45 degrees west of north. We could also call that northwest because that is flat out in the middle. We can actually give that an actual direction. But I'm just going to call it west of north for just our giggles. Alright, so I can take these and I can draw them all out individually. So let's take the first one. And we're going to kind of show what's going on here. Now this is 37 degrees east of north. So if I draw my coordinate system on that first one, I'm going to end up with something that's going to be kind of out here. Okay, now that's 1.7 kilometers. Now, I want to draw each one individually because we're going to add them later. So when you see this next one, don't just freak out, but I'm going to draw another coordinate system. And I'm going to go 0.9 kilometers at 14 degrees south of west. So I'm going to go back to the 0 point, I'm going to go back to our origin, and we're going to go south of west. So here's our west, and we're going to go 14 degrees. Now that's 0.9, so it's going to be smaller than our 1.7, so I'm going to make that a little bit smaller. There's our 0.9. Now, just because my numbers are off here, just look at it up top, look at some of your previous stuff. If you need to look at those numbers a little bit clearer. I'm going to try to fit everything in here, though. All right, the next one. I want to draw the same thing here, and I've got 4 kilometers due north. Okay, so now this one's going to be much bigger. I'm going to draw this a little bit fatter, I think. I'm going to try to. And it's 4 kilometers straight up. And then our last one, we're going 2.1 kilometers at 45 degrees west of north. So west is in this direction or the negative direction. And we're going to go 2.1 kilometers. So that's about half of what we were. All right, so now I've got all these individual vectors. Now we want to take and we want to add them together. Now I could get a very good graphical representation and take all these and do the tail to tip if I had graph paper and I did everything perfect. But sometimes we screw things up when we put things on graph paper, and we don't want to do that. We want to actually get a good mathematical answer. So since this is a trig-based physics class, I'm going to show you what we're going to do. I'm going to take this out real quick, and I'm going to go and I'm going to put these in a little bit different representation. We're going to go from here and put them into triangles. And fast forward to the future, we've now got everything drawn out into the coordinate systems individually, but now we're going to break it down, and we're going to go into more of a geometry look at this, and we're going to put everything into triangles. Now everybody knows that the right triangle is the easiest triangle to work with. So what I'm going to do is I want to make a right triangle, even though in this, when you're moving from one direction to another, you're not going at right triangles, but if I change the origin to 0 at each one, I can make each one a right triangle. So what I'm going to do here is I've made each one an origin of 0, and we've made a little right triangle at each section. So I'm going to draw those right triangles. That's my 1. That's my second one. Now my third one's not a triangle, it's just going straight north, it's going due north, so I really don't need to draw a triangle. And for 4, it doesn't really matter which direction I draw here because it's still going at 45 degrees, so each way would be the same. Okay. Now, since we are talking about geometry here and we're dealing with triangles and dealing with right triangles, we want to make sure that we know about Chief SOHCAHTOA. Okay, so everybody knows about SOHCAHTOA by now, I sure hope. But just remember, just a refresher, everybody needs a refresher. We have sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. Okay, so it's very handy. We'll actually probably use tangent on the very, very last problem. Okay, so what we have here is we know the hypotenuse of all these triangles. Okay, so we're sitting at 1.7, 0.9, 4, and I'm sorry I did not write that down. We are at 2.1 on the last one. All right, so when I look at these triangles, I know the angles of all of them. My first one, I'm at 37 degrees here. So I have to be careful about which way I draw it. The triangle I drew from in this direction, so since this is 37, I have to make sure that I write the other one correctly. This angle is going to be 53, and this corresponding angle would have been the 37. Okay, on this particular one, I did set it up the way I wanted it to, and that's going to be at 14 degrees. Okay, this one's at 90, so it's all set up, and then the bottom one is at 45, so it does not matter because both of them are 45, and that's kind of awesome. All right, so the first one, I'm going to solve for x. So my x is right here. When I solve for my x, that's my adjacent side. Okay, so since that's my adjacent side, which one I'm going to use? I'm going to use so, am I going to use ka? And since it's adjacent, I'm going to use the ka. Now I'm going to do the math on my calculator. I've already done it ahead of time. If you guys need to pause this at any time, make sure you're taking the time and pausing the video here and work this thing out. I'm just going to start plugging numbers. It's going to go pretty quick here. So I've come up with an x of being 1.02. Now, I'm not doing any sig figs or anything crazy. I'm just going to go and kind of give some good solid numbers. I'm not going to take it out too far, though. Okay. When I do my y, I'm going to do a sign here to get my y, and my y is going to be 1.36. Okay. Now my x, now I got to be careful on this. My x is going to be in a negative direction, okay, because it's going to be going west, and anything that's going west is going to be considered to be a negative direction. So when I write this, I'm going to solve for it just like normal, but when I solve for that, that's going to give me a 0.87. I have to manually come back and make sure that I put the negative there, because that's just a representation of which direction it's going. Okay, I'm going to do the same thing for the y. When I do the y, when I solve the y, it's also going in a negative direction because it's going south. So when I do the math on that, and my y is going to be my opposite, so that's a sign as well. So what I have there is a 0.21, and I also have to put a negative there. All right, the third one. The third one is super easy. These are great. These are the ones I look forward to, because when I look at that, all I have is a y. My x is 0 because it's not going in the x direction, and my y is going to be 4. So just exactly what I have. It's going in the positive direction, so I just leave it as a positive 4. Okay, now the fourth one, I have a negative and a positive. Okay, my x is going to be moving in the negative direction, so when I solve for my x, which is going to be my sign there, when I solve for that, I end up with a 1.48. I have to manually go back and make sure that I put that negative in there, because I need to make sure it's going in the negative direction, that west direction. Okay, y though is going in the positive. Now when I solve for this, okay, since 45 is the same on both sides, it doesn't really matter. It's the same answer. So it's 1.48. But in this case, it's a positive. All right, I've got all the individual components done now. So you'll notice on the bottom I have written x total and y total. Because if I take all my x's and add them all up, and I take all my y's and add them all up, it's going to give me my final point, my final displacement. So I add all those up, and I have an x total of negative 1.33 and a y total of 6.63. Now what that tells me is my x total, I'm going to end up going west, because that's going to be on the negative coordinate there. My y total is going to be a positive direction, so that's telling me I'm going north. And we're going to have to go and draw that. All right, so we now have a coordinate system that is the components of all of them put together. So we've added all our vectors, and I've placed them where they would fall. We said our x was a negative 1.3, so I've gone ahead and I've placed it roughly where negative 1.3 would be. And our y is at 6.63, and that's a positive 6.63. So if I take these and I extrapolate to a point, I should be way up there. Now if I draw a line... Alright, this is where Zach put his finger over the little button that tells you like the sound. So basically what we have here is, I'm going to dub this now like it's an old kung fu movie. Okay, so I'm going to draw the lines. You'll see that I notice I have a negative 1.3 and I have the 6.63. And I've drawn a resultant line. Okay, that resultant line is actually where we are going. Okay, now I'm going to set an angle there, and I'm going to do that through a tangent. Now I can't divide by tangent, so I have to do an inverse tangent here. Awesome, because I know I'm at 1.33 here. And I know this side is 6.63. I can solve for it another way. I'm not going to actually do that. That's kind of a pain in the rear end. Our tangents are actually solid set numbers here. So if I do an inverse tangent and I actually solve for the direction of which way we're going, I will see that we're going 11.3 degrees west of north. Which, if we look at this, that's about where it's going to end up being. That's a pretty good graphical representation of where we're at. Now, when we solve for the actual thing, I didn't solve for it. I solved for it ahead of time, though. If I solve for the resultants using the Pythagorean theorem, what I end up with is 6.76 kilometers. I'm going to put a unit to that, and it's going to be at 11.3 degrees west of north.